Hi, everybody. Today I'm going to talk to you about the law of conservation of momentum. Law of conservation of momentum is the first of the big conservation laws that we'll learn about in physics. It is an easy one, I think, once you kind of wrap your head around it. It's an easy one to understand, especially in the one-dimensional cases that we're going to kind of confine ourselves to. So here we go. Again, it's the law of conservation of momentum, and so it's important to be able to remember what momentum is before we start. So remember, momentum is what we defined as inertia in motion. And so it's defined by this formula here. The momentum, little p, which I know is weird, is equal to the mass of the object multiplied by its velocity. Now, don't forget that because velocity is a vector quantity, momentum is also a vector quantity. So it's important to remember which direction this momentum is going. We are going to confine ourselves to a one-dimensional situation, and so really there's only two possible directions that you could go. You could go to the right, which we will typically define as positive, or to the left, which we will typically define as negative. We could turn that so that we have an up and down situation, but for the most part, as we do our exploration, it's going to be to the right, positive, and to the left, negative. Okay, so the law of conservation of momentum states the total momentum in a system is constant unless the system experiences an external impulse. Now, there's a lot of terms in there that might be a little technical or confusing, so I want to make sure that you guys have kind of a breakdown of those. We just talked about what momentum means, so I'm not going to worry too much about that. I do want to point out that it is the total momentum, so you have to add all of the momenta together, and momenta is the plural of momentum, so just keep that in mind. If I say it, I'm not saying it wrong. That's just the way that we say more than one momentum. So the total of all the momenta added together, so all the positives in this direction, all the negatives in that direction, added together is going to give us the total for the system. So first off, we have to understand that it's the total momentum. Second, it's in a system. So what the heck is a system? We have to talk a little bit about that. So a system is defined as a part of the universe that we can study as if it was its own isolated setup. And so it could be anything that we want. It could be any system, any object, any set of objects that we'd like. We can kind of draw an imaginary boundary around the object or set of objects and then imagine that we can analyze things without any reference to anything outside of that system if we wanted to. So I'll give you an example. Let's imagine for a minute that you were in a car. All right, so here's your car, and here's you inside, right? So there's you inside, driving along, everything's great. What's the system here? It can be anything that we decide. We could decide that the system was just you if we wanted to. We could decide that the system was both you and the car. We could decide that the system was both you and the car and the earth below you if we wanted to. Now, just like before when we talked about the frame of reference, and your choice of frame of reference can make your life a little bit easier or a little bit harder if you're smart about it or not smart about how you do it. The same thing goes here with systems. So how you define the system is going to make your life a little bit easier or a little bit harder if you are not careful with what you're doing. So in this case, it all depends on what kind of motion we're talking about, whether we should define the system as the person or the person in the car or the person in the car and the earth. We could go further if we wanted to, but really there's typically not much reason for that. So we could say the person in the car, the earth, and the moon. But really the moon's influence has very little impact on things. So systems, again, are things that we can define, but they should be intelligently defined. So you should really think through what that looks like. We're going to talk about how to think through that. So I put a situation on the board, and I'd like us to think about it if we could. We have a blue card here, and the blue card has a mass of 1 kilogram, and it is moving to the right. Notice the positive here. It's moving to the right at 3 meters per second. So if we wanted to, we could calculate the momentum of just the blue card. And so we remember that we multiply these two together to get the momentum. And the momentum is equal to the mass times the velocity, which gives us a positive 3 kilogram meters per second. Now let's compare that to the momentum of the red cart. Now the red cart's on the same track, and they clearly are going to collide in just a minute, and we're going to talk about what happens when they collide. So let's take a look at what its momentum is. Notice it has a larger mass. It has a mass of 2 kilograms, so it's going to resist a change in its motion more, so that's important to remember for later. And it has a velocity that's to the left, note the negative sign right there, of 2 meters per second. And so to figure out the momentum, I just multiply those two together. P equals m times v, or 2 times negative 2, for a total of negative 4 kilogram meters per second. So which one has more momentum? Well, clearly the red cart has more momentum, but it's in the left direction. So don't forget that the negative and positive just means the direction. So which one, if I ask you, had more momentum, you could say it would be the red cart, because technically it does. I'm not worried so much about the sign. So what happens when they collide? Well, we could analyze this in 3 different ways. We could talk about just the blue cart is the system that we're working with, or just the red cart is the system that we're working with. Or we could talk about the blue cart and the red cart together as a total system. And I think you're going to find that the last one is probably the best case for analyzing the motion after 2 things collide. Okay, so let's take the blue car as the system by itself initially. So if I take the blue car by itself, we know that it has a momentum of positive 3 kilogram meters per second. But we know that the red car is going to hit it. And so it's going to apply a force over a certain period of time. Now don't forget that a force applied over a certain period of time is an impulse, right? Force times the change in the time is the impulse. I think you'd agree that because this is a vector and this is a vector, we could say that the impulse was in this direction from the red cart. And so that impulse comes from outside of the blue cart system. So if you look at just the blue cart, all of a sudden this thing comes in from outside of the system and applies an impulse, and it's going to change its momentum. And so that's going to be a little bit harder to analyze mathematically. And so we typically don't want to do that if we don't have to. And so again, not the best case, because we have what's called an external impulse, an impulse that's coming from outside of our blue cart system. So now let's take the red cart by itself. As a system, is it the best choice for how we define things? And the answer to that is no, as you see. So the system itself has a certain amount of momentum. The red cart, we know, has a momentum of negative 4 kilogram meters per second. But the collision occurs and the blue cart applies an impulse. Because the blue cart is outside of the system, it's an external impulse, and so it's not something that we can take into account very easily. And so as a result, we know we have this impulse, and the impulse is going to be in this direction. And that's because the blue cart applies a force over a period of time. Now the question is, compared to what we were just talking about, the force that the red cart applies to the blue cart, these forces should have the same strength or the same magnitude. And these times should be the same because they impact at the same amount of time. And so the impulses are really going to be in opposite directions. They're going to be the same size impulse, but in opposite directions. And so it's much better if we take a step back and say, let's take both carts into account when we're talking. Okay, so now we've defined the system as both the blue cart and the red cart. And so we can actually employ, in a much smarter way, the law of conservation of momentum. The law of conservation of momentum says, if there's no external impulses, and there really isn't on this because the normal force from the tracks is canceling out the gravitational force from the Earth, there's nothing coming in from outside that's causing an impulse, in this diagram at least, on the 2 carts. And so as a result, we can say that inside of that system, this little artificial boundary that we've drawn, inside there, the momentum is going to be constant, the total momentum. Well, how much momentum do we have? Well, this one has, the blue cart has a positive 3 kilogram meters per second, and the red cart has a negative 4 kilogram meters per second. And so if we were to add those two together, you would see that the total system momentum, right? So the total momentum, the sum of all momenta for the system is +3 plus -4, or -1 kilogram meters per second. So -1 kilogram meters per second. So what the law of conservation of momentum says is that no matter what happens inside of that system, this number will never change. So if we know the momentum of one of the objects after they collide, we can figure out the momentum of the other object. And typically we then use that to figure out the velocity of it. If you get it, you can go ahead and turn the video off at this point. I'm just going to try to finish up that example. So remember that the sum of all of the momenta in the system, inside the system, is -1 kilogram meters per second. So let's imagine that the blue cart we measure to have a velocity, a new velocity, after the collision of -6 meters per second. So how can we use that to be able to figure out what the new velocity of the red cart is? Well, the trick is that we use the law of conservation of momentum so that this number is never going to change inside the system. And so we need to be able to calculate what the momenta are for both of the carts. So for the blue cart, it's still mass times velocity, or 1 times -6, which gives us a new momentum of -6 kilogram meters per second. So here's the trick. I know that I have to get -1 total, and I have -6 here. So what do I have to add to -6 to get a -1 answer? The answer, I hope you can see right away, is +5. So if I get +5 kilogram meters per second here, -6 plus +5 gives me -1, and that then satisfies the law of conservation of momentum. But if I want to get +5 kilogram meters per second momentum here, what velocity do I have to multiply by 2 to get the 5? And I hope you can see that the answer there should be 2.5, and that's a positive meters per second. And so by using the law of conservation of momentum, I can figure out what the velocities are at the end of our collision. And we'll be doing that in some experiments as the week goes on. Thanks for watching.